Hi everybody. So in this video, we're going to look at solving a range of modulus problems. So we'll combine our work on transforming functions with a modulus function, and we'll look at the domain and the range. We'll work through a couple of examples, and you can download a copy of this PDF from my website if you want to work along with me. So if we begin with example 1, we've been given the function f of x, which is given here, where x is a subset of all real numbers. For part A, we need to draw a graph of this function. So I'll sketch the axes. So when you sketch a function like this, we start with the x term and then we keep building it up. So if I draw the line y equals x, then the next thing we need to do is translate this 2 units to the left. This will give us the x plus 2. And as we continue to build it up, we need to label the coordinates on the axes. So this point will be when x is negative 2, and this point will be when y is positive 2. And now we need to sketch the modulus of this line. So these negative values of y will be reflected through the x-axis to become positive. And these positive values of y will remain the same. So now we have y equals the modulus of x plus 2. So now we need to stretch this by a scale factor of 2 in a direction parallel to y. So this value will become positive 4, and this point will become invariant, because when you double the 0, we get 0. So you can see that the graph compresses. And then the last thing we need to do is take away the 3. This will be a vertical translation where we move everything down by 3 units. So on this point, we'll go down by 3 units to positive 1, and this point will be translated to negative 2, negative 3. So this will be our function of x. And I'm just going to draw this separately to keep it tidy. And then for part B, state the range of this function. Well, the range considers the y values, and you can see that our minimum value of y is at negative 3. And because x is all real numbers, the values of y will continue to increase infinitely. So our range is f of x must be greater than or equal to the negative 3. And then for part C, solve the equation that f of x equals x plus 1. We know f of x has a gradient of positive or negative 2, and this gradient of 1 would be less steep. And this will also have an intercept of positive 1. So it would look something like this. And this will give us two solutions. One where we've got the positive case of the function, and one where we have a negative case of a function. So to find this value of x, we need to consider the negative case. So this will be the negative of x plus 2. And we can write this as negative 2 here. Then if we expand this out, so we'll get negative 2x minus a 4, take away the 3, will equal x plus 1. Negative 2x minus the 7. We'll move a negative 2x to the right-hand side, and this positive 1 to the left-hand side. So negative 8 will equal 3x. So x will equal negative 8 over 3. Okay? That'll be this point here, negative 8 over 3. And then to work out this solution, this will be the positive case. We can see this will be at when x equals 0. But if we just solve the equation to make sure, so the positive case is when this term is positive. So we'll get 2x plus 4 minus the 3 will equal x plus 1. We'll move this x to the left-hand side. Then you can see that the 4 take away 3 is equal to the 1. So x will equal 0. Okay? So like I said, when we sketch the graph, it's really important that we label the coordinates. This will help to make solving the equation much more simple. Let's try the next question. Okay, so for example 2, we've been given this function f of x, and in the domain x is greater than or equal to 0. Before you work through a, b, and c, try and find the coordinates of this point and the y-intercept. That will help with these 3 questions. You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So the first thing that we need to do is to work out these 2 coordinates. If we begin with this one, we know that x will be 0. So this will give us f of 0 will be 2 lots of 3 minus 0 plus 1. And 2 times 3 is 6, and for 1 is 7. So this point will be at y equals 7. And then from this point, we know this is the minimum. And the smallest that the modulus of a number could be is 0. So this x value must be 3. So I label this here. And then when this is 0, we double that to get 0, and we add 1. So this point would be positive 1. And then for part A, state the range of f of x. Well, we know that x is increasing beyond 0, and that the minimum y value is at positive 1, and as x increases, y will increase. So our range is that f of x must be greater than or equal to positive 1. It can be equal to 1 because x can be equal to 0. And then for part B, solve the equation that f of x is x plus 4. Well, if we sketch x plus 4, it will have an intercept between the 1 and the 7, so about here. And the gradient will be less steep than the function of x because this has a gradient of positive or negative 2. So I'll draw on it something like here. So our values of x will be at this point and this point. This will be the negative case because when you multiply this by the negative 2, we get a positive gradient. And this will be the positive case. You can see this has a gradient of the negative 2, which is from the 2 times this negative x. So I just label this as the negative case, and this one as the positive case. We'll begin with the positive case. So this will be when f of x will have the 6 minus the 2x plus the 1 will equal x plus 4. We'll solve this equation. We'll move a negative 2x to the right-hand side. And we get the 6, add the 1 to make 7. We'll take away this 4, and we'll get 3. So x will equal 1. I'll label this on the graph here at 1. We'll expand the brackets out again. This time this is a negative 2, so we get negative 6 plus the 2x plus the 1 will equal x plus 4. We'll move this x to the left-hand side. Negative 6 add 1, negative 5, which will move over to the right-hand side, and we'll get 9. So x will equal 9. Okay? And then for part C, given that the equation f of x equals k, where k is a constant, has 2 distinct roots, state the possible set of values for k. So we know this will be a horizontal line parallel to the x-axis. We know that when k equals 0, we'll have no roots. But as we continue to increase k, when k equals 1, we're on the minimum of f of x and we have 1 root. And if we increase k further, now we have 2 roots. And we continue to have 2 roots up until k equals 7. If we go beyond that, we have 1 root again. So k must be less than or equal to the 7, but greater than the positive 1. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.